Today's lesson is on statistical studies and distributions. There are different types of statistical studies. The following are some common methods of data collection: sample survey, observational study, survey, and experiment. Broadly speaking, a survey is a way of learning about a group of people by having some of the people in the group answer questions. It might involve completing a form, completing a questionnaire, or participating in an interview. An observational study is a type of study where a researcher uses observed information to learn about a group of individuals. The individuals being observed are specifically not interfered with, aside from the measuring of their responses. For example, if we wanted to learn if a person's hair color is related to his or her favorite soda, we would record values of the variables hair color and favorite soda from observation or from reported observations. A sample survey is a study that is carried out using a smaller group of people who are intended to represent a larger population. For example, if we wanted to know more about the opinions of the 1 million adults who live in a particular city, we could randomly select 900 individuals from those 1 million and conduct a study. Well-designed studies of this type can provide data that can be used in a variety of ways. For example, it might be used to assess the views of the general public, to examine trends in customer behavior, or to estimate the values of population characteristics when a census of an entire population is not practical. Lastly, an experiment is different from all other studies because now the researcher deliberately imposes different treatments on different groups and then compares the groups to determine if there is any difference in a specific variable of interest called a response. A well-designed study of this type allows researchers to decide if the different treatments result in different responses. Using the previous descriptions, determine if each study is a sample survey, an observational study, or an experiment. A pharmaceutical company is interested in comparing 3 brands of pain relievers. The company wants to know if one brand is much better than the other brands in terms of mobility improvement. 3 different groups of 30 people participate in the study. Each group gets one of the 3 brands of pain relievers. The improvement in mobility of these 90 people is recorded after 5 weeks of taking the medicine. In this example, the key words to note are the fact that we have 3 different groups of 30 people. We're giving each group one of the 3 brands of pain relievers, and what we're doing is recording the improvement in mobility. This would be an example of an experiment, and the reason why is because now we are deliberately imposing different treatments on different groups. We are actually having some kind of response. We want to see what is the improvement in their mobility. Example 2. Medical records of a group of longtime residents of a town are compared to the medical records of a group of longtime residents in another town. Researchers are curious to see if one town appears to be healthier in general. Well, what we're doing is we're taking these medical records and we are simply just comparing them to medical records of another town. This wouldn't be an example of an observational study. It's an observational study because all we're doing is simply comparing medical records of 2 different towns. We're not imposing any kind of treatment on these people. We are specifically not interfering with these individuals. Example 3. A group of 600 registered voters in a given county are asked how they intend to vote in an upcoming election. A summary of their responses is posted on a news website, and it is implied that this group is representative of all registered voters in that county. The responses are used to predict the outcomes of the election. Our key words are group of 600 registered voters and representative of all registered voters in that county. Therefore, this is an example of a sample survey. This is a type of study that's carried out by using this smaller group of 600 registered voters in order to represent the entire population. Example 4. In a study to see if administering a medication orally or by injection makes a difference in how quickly people with back pain feel relief, A group of 400 adults suffering from back pain is divided into two groups. One group of 200 people is given the medication in pill form, while the other group of 200 people is given the medication in the form of a shot. Results for each group are compared to see if there's a difference in pain relief between the two methods. Our keywords here would be administering a medication, whether it was orally or by injection. The fact that we have these 400 adults that's divided into two different groups who are receiving different types of medication, either in pill form or in the form of a shot. All of this would allow us to know that this is an example of an experiment. It would be an experiment because we have different treatments on our different groups. And what we're doing is we're measuring the response. Our response specifically being if there's a difference in the pain relief. Why randomization matters. Randomization plays an important part in data collection in two distinct ways, either random selection or a random assignment. Random selection, in the case of a sample survey or observational study, we want the sample of people involved to be representative of their greater population. To help achieve this, we want the people to be impartially selected so that we do not introduce any favoritism in the selection which could potentially distort conclusions drawn from the data. Random assignment. In the case of an experiment, we want to impartially assign the people, called subjects, to the various treatment groups. If we do not do this, we might inadvertently create a situation where any observed differences between our groups may have been caused by some factor other than the treatment in which we are interested. The 4 studies that we previously looked at are actually presented again. However, additional information is now provided regarding how these people involved were chosen or assigned. Each of these studies contains a flaw in terms of how the people involved were chosen or assigned. For each study, explain why the data collection method might result in bias, and suggest how randomization should be properly employed to eliminate the bias. In the first example, we had 3 different groups of 30 people participate in this study, and they're given 3 different brands of pain relievers. We're now told that the first group of 30 patients were patients of Dr. Winkler, the second 30 were from Dr. Singh, and the last 30 from Dr. Manganon. The reason why there is bias here is because there is no random assignment. In order to eliminate the bias, what we must do is randomly assign all 90 patients to each pain reliever until all groups have 30. In example 2, we were comparing the medical records of 2 different towns. The additional information: in order to save time and money, all of the records were selected from the largest of the 4 hospitals in town X and from the largest of 3 hospitals in town Y. So of the 7 hospitals, we are only looking at records from the 2 largest hospitals. This clearly has bias as well. This one has no random selection taking place. We are selecting it specifically from one particular hospital in each town. In order to eliminate this bias, we must randomly select samples from all the hospitals in town X and town Y. Example 3. The additional information that's given to us is that these 600 voters were submitting their opinions via a web page and were able to choose to participate after seeing this advertisement on television. So there's clear bias here because the only people that were participating were those who saw the advertisement on TV. Therefore, in order to eliminate the bias, one possible solution to this could potentially be mail-in polls with surveys that are sent to homes. Although one can argue that there is still some slight bias due to there being a homeless population that will not receive a mail-in poll at home, this is probably still the best way that we can eliminate as much bias as possible. Although this may seem a little archaic in this time of technology, it's still the way that we can get the most reach. This is why the U.S. Census Bureau is still done the same way. Example 4. The additional information that we're given here is that people were actually allowed to select how they wanted to take the medicine, whether they wanted it in pill form or whether they wanted it in the form of a shot. This clearly has no random assignment. There is bias that is occurring because they're simply just choosing what pain treatment they want to receive. In order to eliminate as much bias as possible, what we can do is randomly assign patients to each group until there is 200 in each group. A manager at Sobeys is interested in the distance Sobeys employees travel to work each day. She asked each employee how many kilometers the store is from his or her own home and received the following answers. It appears that she surveyed 50 of her employees. And for the data, what we're doing is calculating each of the following: the mean, median, mode, standard deviation, min, max, range, Q1, Q3, and the IQR. Hopefully these are terms that are familiar to us from our statistics unit in Math 1. As a little refresher, measures of center. To calculate the mean, we would add up every single one of the kilometers and divide it by the total number, which is 50. That would give us a mean of 7.86. The median can be found by listing all of the data values in order from least to greatest and finding the exact middle of that data set. Mode. It's the number that appears the most often in our set of numbers. In this case, the numbers 2, 4, and 5 each appear 5 times. So I'm just going to say that there is no mode. The minimum, the smallest number in our data set, is the number 1. Maximum, the largest number in our data set, is 18. Quartile 1. It's the middle number in the first half of our data set. So once we had our numbers lined up from the smallest to the greatest, and I found the median, which was quartile 2 at 7, all the numbers from 1 through 7 that are still in a row, I would find the exact middle number, which is 4. Quartile 3 is of the second half of the data set, the exact middle number, which is 11. The 3 measures of spread that we have learned about include range, IQR, and standard deviation. Range, that would be the maximum minus the minimum. IQR can be found by taking quartile 3 minus quartile 1. So 11 minus 4 is equal to 7. Standard deviation. Standard deviation measures the amount of variation of our set of values. So standard deviation, last year you learned as a formula, it was equal to the square root of the summation of each individual data value minus mu, which represented the mean of our data set, quantity squared, divided by n, which was the size of the population we were looking at. I'm not going to have you calculate the standard deviation on your own. That is, on average, how far is each data value away from the mean. For this data, what we're going to do is create a histogram. Last year, you learned that in order to do that, we needed a minimum of 5 intervals. It could be a minimum of 5 up through 20 of them. The distance intervals I'm going to determine by looking at my minimum and maximum. It looks like it goes from 1 to 18, so the distance intervals could be just every 3. It would be from 1 to 3, 4 to 6, 7 to 9, 10 to 12, 13 to 15, 16 through 18. Just a reminder that your distance intervals can vary from mine. I just wanted to make sure that I had a minimum of 5 intervals. Frequency, or the number of times that number occurs. Looking back at your data set, what you're doing is counting how many times the numbers 1, 2, and 3 appear. It happens a total of 10 times. I'm going to continue and count them up and list them in the second column. The relative frequency would be a proportion. I would take the frequency, so the number of times 1 through 3 occurs, 10, out of the total 50 data values I have. 10 divided by 50 is 0.2. Continue that for the rest of your distance intervals. Next, go ahead and label and scale your axes for your histogram. Now that you have your axes labeled and scaled, go ahead and complete the rest of your histogram. What do the values of the mean and the median tell you about the distribution of the data? Because our mean was greater than our median, this suggests that the data is skewed to the right. This also means that there are probably some data values that are pulling the average higher. The second part of that question asks you to explain how the histogram justifies your answer. In the histogram that we have here, we notice that if we were to draw a curve over our histogram by finding the midpoint of each of our bars and connecting these together like we did last year, we have a skew that is slightly to the right. The histogram is confirming to us that the data is not quite symmetric. Describe the distribution if x bar, or the mean, is greater than the median, x bar is equal to the median, or x bar is less than the median. When our mean was greater than the median, this was an example of a right skew. Our histogram would match the one that we see above. In this case, we would have a mean that is greater than the median. If the mean were equal to the median, then we had what appeared to be a symmetric distribution. The mean and the median were both equal to one another. And lastly, if the mean was less than the median, then we had a left skew distribution. Here, this would be the mean and the median. We're going to now use a curve to model a data distribution. We will use the following example of a symmetric distribution to dig deeper into histograms. A paleontologist studies prehistoric life and sometimes works with dinosaur fossils. The table below shows a distribution of heights, rounded to the nearest inch, of 660 compies. The heights were determined by studying the fossil remains of the compies. We're going to start with some of our analysis questions, starting with number 1. What does the relative frequency of 0.136 mean for the height of 32 centimeters? What this means is that of the 660 compies that we have in our sample, 13.6% of them measure 32 centimeters in height. This also means that in terms of a probability, if we were to choose at random, we have a 13.6% chance that we select a compy of 32 centimeters. 2. What is the width of each bar? What does the height of the bar represent? What is the area of the bar that represents compies with a height of 32 centimeters? The width of each bar is 1 centimeter. The height of each bar represents its relative frequency. And lastly, the area of the bar represents the relative frequency of the bone measurement within the bar width interval. 3. The mean of the distribution of compy heights is 33.5 centimeters, and the standard deviation is 2.56 centimeters. Interpret the mean and standard deviation in context. Well, we know that mean means average or typical, so the average or typical compy height is 33.5 centimeters. And standard deviation. If standard deviation is a measure of the amount of variation of our set of values, then we can state that a standard deviation here of 2.56 centimeters is the average distance away from the average compy height. Four, mark the mean on the graph and mark one standard deviation above the mean and one below the mean. To do that, let's go back to our graph. If this bar represents 32, this bar represents 34, then here would be 33, and I'm going to assume that right about there is 33.5. So labeling that, x bar is equal to 33.5. If our standard deviation is 2.56, then what I want to do is add 33.5 plus 2.56 to get 36.06. 36.06 happens right about here, and that would be x bar plus 1 standard deviation above the mean. At, again, 36.06. Then one standard deviation below the mean, 33.5 minus 2.56 would equal 30.94. 30.94 would be roughly around here. X bar minus one standard deviation, 30.94. The next part of number 4 asks in letter A, approximately what percent of values of the dataset fall within one standard deviation away from the mean? Well, looking at our graph, we want to determine between this one standard deviation below and one standard deviation above, what percent is in between the two bars. To do that, what we can actually do is use our relative frequency table. Because all of our heights are given to us in integers, I'm going to do my best to approximate it as best as I can. So 30.94 would probably include all of 31. So 31 has a relative frequency of 0.091, all the way up until 36.06, which includes everything up through 35 as a height. So between these relative frequency values, I would add up and total for number 4, letter A, what percentage of compies lie between one standard deviation below and above the mean. When I added them up, I got 0.667, which means that about 66.7% of compies are between 30.94 to 36.06 centimeters. Now that we've answered letter A, in letter B, mark two standard deviations away from the mean, above and below. Approximately what percent of values in this dataset are within two standard deviations of the mean? Again, going back to our graph and our relative frequency table. From the mean of 33.5, I'm going to add 2.56 plus 2.56 to get 38.62. And that would be two standard deviations above the mean. Repeating this process, 33.5 minus 2.56 minus 2.56 is equal to 28.38, and that would represent X bar minus two standard deviations. To find the percent of values between the two green bars, which represent two above and below from the mean, I'm also going to use my relative frequency table. I will be approximating the relative frequency since we do not have integers for our standard deviations above and below the mean. 28.38, I'm going to take everything starting at 29. And then for 38.62, everything including up through 38, and add all of these frequencies together. When I added them all up, I got 0.946. So going back to answer this question, between 28.38 to 38.62 centimeters include about 94.6% of our compies. 5. Draw a smooth curve that comes reasonably close to passing through the midpoints of the tops of the bars in the histogram. Shade the area of the histogram that represents the proportion of heights that are within one standard deviation from the mean. To the best of my ability, I'm going to draw a curve that goes through the midpoints of each of the bars of my histogram. And now shading the area of the histogram that represents one standard deviation of the mean would be everything here. Six. Based upon our analysis, how would you answer the question, how tall was a compy? I would say that a compy had an average height of 33.5 centimeters with a standard deviation of 2.56 centimeters. Or I would say that most 95% of compies are between 28.38 to 38.62 centimeters.